All right. All right. And I'll be repeating the question so that the question is recorded in the video as well, because the chat window is not visible in the recordings. All right. So I'll be repeating the questions uh, you know, before answering it. All right. So let's start now. So today we have 10 members. There's some more would be joining soon. All right. So hello everyone. I am Sandeep Giri from No Big Data, as we had discussed last time. And so should we do a recap, or are you okay with the architecture of Hadoop? All right. So okay. So please participate in the chat. Okay. Ask questions and as much as you can, so that it's more interactive for all of us. All right. So last time, in the last session on 21st February, we discussed about the architecture of HDFS. Okay. Now, the architecture in that architecture, there was something called name node and there was something called data nodes. Data nodes keep the actual data. Name nodes just keep the metadata, such as directory structure, folder names, the name of the files, size, attributes of the file, and all of that. And name node was maintaining the metadata in the memory for the faster access. And also, name node delegates any request it comes to name node. It keeps on delegating it directly to the data nodes if the request is for the actual data. Okay, so for example, when you download a file, the first request will go to name node. Name node will figure out which file is it, and based on that it will figure out what are the various blocks of that file, and where is that block, where are those blocks located on the cluster, and what are their what are their copies, the copies of the blocks, and where are those copies of the blocks located. So all of that name node will figure out and will direct the client to the various data nodes. Now, a- any further communication happens between the data node and the end user and the client. All right, so this is how it works. All right, so Saicharan's question is, how about systems working before big data started? How do they handle large amounts of data? So before, those companies who were maintaining similar size of data, what we have today, what kind of data is handled by, say, Hadoop, those companies had their internal tools similar to what we have now in public. Okay, so they did have some tools. They did have some amount of, the not as sophisticated as Hadoop, but there were some kind of a tools they were trying to manage. For example, we discussed the architecture of 100 terabyte data, right, in the last session. So let me just go back a bit. All right. So say for example, this was the common architecture to for the larger storage. Okay. So there were similar kind of systems earlier, and people had built their own kind of systems. And for smaller data, for smaller unstructured data, everything went into database. While for the larger data, people went for this kind of a file system. Also, some of the people who had to store a larger data, what they did was they did sharding. They did sharding using multiple databases. Okay. So, for example, at one of the organization I worked with, we did we had say 20 installations of Postgres, and we divided the data among these 20 instances of the databases based on some ID. So some of the data went to one, some of the data went to another, and so on. Okay, so we had built this manual kind of a sharding system where we have you know figured out that which ID data will go to which server. Okay, so that's how we did. Was he able to answer as I? Yes. Can you hear me? How did the data accessing handled in that older system you explained? Right. So the way we have divided the file system here, the data accessing looks like Sai Charan is offline. So Roshan, are you talking about this one or the other? Yeah. In these cases, there is a main folder and there are multiple. Oh, yes, I actually we did cover. Okay. All right. So in this one, in this one, this is the older way of doing things. Here there is a main folder. There are multiple hard disks. User comes to the main folder as in end user and figures out where is the data kept and then accesses it. Okay. And most of them actually maintained an index of which file is where. And that index would be maintained somewhere in a file or in a database. Okay. So the other way was to have a database maintaining the list of files and which server is it located and so on, much like a name node. Yeah. All right, so should we go ahead? All right, so and having a sharding server was a common architecture, as in you will have, say for example, let me just draw some things. So there would be a, let's say that this is your user. Okay, this is your user, and user comes to one of the using APIs, it comes to one of the indexes, and so let's call it index server, or maybe an index table, and based on that there are say MySQL1, and all right, so then there is MySQL2, MySQL3, and let's say for a country like in and we are storing the you we are storing the data for each country separately. So let's say this is for India, this is for US, this is for say UK. So and here you can think of it as maybe some sort of a layer which we generally had an ORM layer which also did this. So this was the general architecture, and lots of people actually follow still the same architecture. All right. It's important to keep this in mind that without having a Cassandra or MongoDB or HBase, you can still manage your data using MySQL or Postgres. Okay, it is very important to keep that in mind, and that is why I'm discussing this. All right, so this is how we generally divided the data, and most of the databases which you will see, that MongoDB, Cassandra, they're built on a similar principle, where this ORM layer, which divides the queries for something, is also absorbed by the database itself as of today. Okay. And the basis of division is an ID in all of these things. Like if ID equals this, then go to my request goes to MySQL. If ID equals to this, then goes to this. And so it is mandatory to have IDs in most of these NoSQLs. No worries. In case you did not understand any of this, we will again cover it in session number 6. Okay, when we were discussing about NoSQLs. All right, so there you go. So this diagram is clear to everyone. All right, so now let's move on. So with this, we have so far discussed how do you store humongous data in files using HDFS. Okay, how do you solve a problem of storage using multiple machines? Now let's discuss something called a compute engine. My question to you is, how fast can 1 gigahertz processor sort 1 terabyte of data? Sorting means ordering the data, and 1 terabyte of data is in the form of 10 billion names, 10 billion strings, and each string is approximately 100 characters in size. And this computer is having a RAM of 2 GB. How fast can such a computer sort such a data? Just give me any number. Okay, couple of hours. Okay, and also think about how your approach. So Okay. So Rohit's question is that sorting times would vary based on sorting method being used. Okay. So let me put it this other way, that you use your best sorting method. You use your best sorting method, and then anyone else? Okay. All right. So it took me around 5 hours. Okay. That was the best that could, you know, so far I could reach to. And why I ask this question is this basically gives you a sense of how it is done. How fast is your computer? Lots of us seem to think that a computer is so fast that it can sort such kind of data really, really fast. All right. So if you have a big table, if you imagine this, if you have a big table having 10 billion names and you want to create an index on this table. If you want to create an index on this table, then it will take more than 5 hours. Yes. So Prithvi's question is that is there a calculation to find out how long the sorting takes? So there are calculations to find that out. But when it comes to handling the data, there are too many parameters. Most of the time actually goes into reading from the disk. Okay. Sorting the data is comparatively faster. But reading the same data which is being sorted takes more time than the sorting itself. And that is why most of the calculations fail when we talk about sorting this kind of data. Alright. So there is a way, but most of that is empirical. And when dealing with the computation of time, you generally deal in terms of the complexity of the your approach. Meaning, if there are n record and your time taken is 1 hour, and if the records become 2n, will it become 4 hours, or it will become 6 hours? How will it go? So that relation between the number of records and time is more important than actual the numbers. Okay. So and most of the sorting algorithms go with n log n. But when it comes to big data, when your data is lying in disk or multiple disks, the actual time goes in reading the data from the disk. Okay. All right. So what we realize is when you have a terabyte of data and you have to sort it, it requires a lot of time. It requires a lot of time. And the problem is that we require faster way of sorting, and we require bigger data. We might have to sort bigger data, and we might have to do it more often. All right. And sorting is probably the most important problem in computing. The whole objective of the database is sorting. Let's have a look at What do I mean by sorting? So if you have, is the font visible to you? So my question is, why am I talking about sorting? Okay, this is very important part. Let's think of a database. What all does it do? When we say select star from my table where x equals to some value, right? Here, what is actually happening here? So we generally, if our data is used, we are going to have an index lookup, right? This will lead to an index lookup, and index is nothing but a sorted values. Okay, index is nothing but a sorted values. Effectively, a select query, the speed of select query will depend on how well is the data sorted. Okay, so select query is again a sorting problem. Okay, because index is a sorted list of things. All right. Now the another problem, another thing which database do for you is group by. Okay, group by is nothing but a sorting problem, right? You sort the data, then you bring all the keys together which has the same name and so on. Okay, then join. Okay, join is again a sorting problem. How? You internally you sort the tables based the key on which tables are being joined, right? And then you join it. Then third problem which any database do is your group by, select, order by is of course. So this is nothing but a sorting. Then order by is nothing but a sorting problem, right? So effectively, most of the data systems, they are built in order to give you a great sorting performance. And that's why sorting is a big challenge for the whole world. There are sorting benchmark websites and people compete in that. And Google has been a clear winner for past few years. For example, on 8 September 2011, Google sorted 10 petabyte within 6.5 hours using 8,000 computers. Okay. Now, how can this kind of computing be distributed? How could Google use 8,000 computers to do the sorting job? All right. So let's get into the details of that part. All right. So that's where the core component of Hadoop, which is compute engine, also it has been called MapReduce in past, although it has been moved to yarn. But let's understand the architecture, because understanding this architecture is simpler, and we will understand yarn architecture after this. Okay, so the core component of a compute engine, that is MapReduce, are again similar to our HDFS. There is a job tracker who is more like a supervisor, and there are task trackers. Task trackers are the actual workers, while job tracker is more like a supervisor, where you go to supervisor and ask, can you get this thing done? Can you get this data sorted? And then that job tracker goes to each of the task trackers and then get the data sorted. Okay. All right. Now the other important part is why this diagram is important is each task tracker is generally running on the same machine on which the data node is running. Okay. And data node, admin node, job tracker, task tracker, all of these are nothing but processes running on the machines. These are nothing but processes running on various machines. All right. So a task tracker is a process running at a particular port on a machine, and generally a task tracker is running on the same place where data node is running. All right. Now, whenever we have to get something done, we go to job tracker, and job tracker delegates it to multiple task trackers. And which task tracker would job tracker generally delegate the work? Okay, it is based on what do you want to process. Say you have a file which is located on data node 1 and data node 2. So job tracker will only delegate the work to data node 1 and data node 2. All right, so that we don't have to transfer the data before processing it. And the merging happens using another task tracker itself. Merging does not happen at the job tracker. Okay, let me repeat some questions. On which node the data merge happens? That is Chandra. So we'll talk about the merging as well. How are the tasks divided into smaller tasks to allocate to different task trackers? Okay, so when we say a task is divided into smaller tasks, it only means there is a logic that needs to be run on each task, each task tracker. The logic remains same on all task trackers, while the data that is processed, say there is a big file that need to be processed, and that big file is allocated on say 10 machines. Some blocks on one machine, some on another, and some on another. So each machine will be executing your task on that data. Okay. So when we say smaller, it means smaller data, not the smaller work. Okay. Suppose we need to perform some action on data from a particular node. Suppose we need to perform some action on data for a particular node. How do admin node and job tracker communicate? Okay. All right. So job tracker knows about admin node. Okay. Just like any other client, just like any other client, job tracker asks admin node about the information of every file it wants to process. Okay. Job tracker and name node should run on the same machine. Not necessarily. Not necessarily. They can be on different machines as well. The only important aspect is the task tracker and data nodes. should be generally on the same machine. Okay, while in the beginning you might like to have job tracker and admin node on the same machine, but in the production environment you generally have job tracker and admin node on different machines. All right. Yes, so job tracker is more or less like a queue manager. Yes, so each node in your production environment need to run task tracker and data node. Yeah, that's correct, Roshan. All right. Now, another presentation of the same thing is there are clients of the job tracker. It has delegated the work to task trackers and so on. Okay. Now let's have a look at what user does. First, you as a user will copy your data to HDFS. Okay. Now you submit your job. You submit your job to Hadoop client. Okay, you give your work, you have written a logic, you have given the work to Hadoop client. Hadoop client now will start processing from here onwards. Okay, so it will first get the files information from the HDFS, and then it will basically upload a job information again onto the HDFS itself, and afterwards it will create the splits based on the information that what are the input files. It will create input splits and then submit a job to the job tracker. Okay, the input, this creating splits is a different game. We'll discuss this part later. Let's avoid this fourth point right now. Okay, because that's a little tricky thing. And afterwards job tracker will initialize a job queue. Just like in a restaurant, you give an order, they create a job queue, or in any of the workshops, they create a job queue in which it is marked that your job is waiting here. Okay. And each job queue, in the job queue, it has the information that where is on which machines is running what. Okay. And the logic is generally divided into two formats called maps and reduces. We'll go into the details after this. Okay. Okay. Sai, let's talk about HBase a little while later. Don't worry about it. Okay. So you have job tracker, and at the same time, the job tracker basically job tracker is maintaining a queue, and each queue in the queue, each element is about who is doing what. Okay, and at the same time job tracker will keep on pinging all of these task trackers and figure out what's going on with them. In case any of the task tracker falters, any of the task tracker gives up, or it doesn't respond to the heartbeat, the job tracker will assign the same work to another task tracker which is closer to the data. Okay, which is closer to the data. All right. So basically, the crux of the matter is the whole diagram. Meaning of the whole diagram here is, okay, as you can see here, is the job tracker maintains a queue noting down what has been delegated to who, and if anyone does not respond within a time limit, it expires it disregards anything done on that machine and reassigns that work to some other machine. Okay. Now the other way we can look at it is this way. Task tracker will handle only one task at a time in a data node. So not really, it will run multiple processes and it will maintain multiple queues. If somebody else has come up and assigned something, at the same time, task tracker will also keep in mind that which data node is busy, and accordingly, in case the another task is required to be run on the same machine because of the data locality, it will avoid it. And instead of running the same task on a machine, it will run it on a neighborhood machine. Okay, it'll run it on a data node which is closer to the data, maybe in the near vicinity, on the same rack and all of this. All right. If a task tracker fails, then there is a chance of multiple job failure. Okay. Yeah, if a task tracker fails here, the same work will get assigned to somebody else. Okay. All right. Now the question comes in that in what form do we talk to MapReduce framework? We generally talk to MapReduce framework when we say that get these things done. We give two things. One is map, other is reduce. Okay. Okay. So Sai Charan's question is, in this case, we will have delay in the solution. There would be a minor delay because all the tasks are happening in parallel. If one fail and gets assigned to another one, there will be a slighter delay. Okay, because the overall time taken by the task will be will be will be the maximum of all the time taken by various task trackers. Okay, is there any limitation on number of task trackers? So ideally you should have the task trackers equal to the number of machines you have. Okay, except for few, say for example, one of the machines you might have dedicated to a job tracker or name node. Except for that, you generally have these task trackers equal in number in to the data node generally. Okay, because running two task trackers on a machine does not make any sense. All right, so when we ask a job tracker that get my work done by task trackers, we give job tracker three things. One, our definition of a function called map. Map is a code. Map is a Java code in the compile format. And another function we give to job tracker is our reduce. Again, reduce is your logic, your code in the compile format. And the third thing which we give to the map reduce, which we give to our job tracker, is where are my files located. Okay, we want to process these files, and how do we want to process these files? Using map and reduce. Okay, now before we go further, let's give it a thought here. So map is a function which describes how your data should be sorted. Okay, and reduce is a function how which describes how your data should be combined. Now, if you have a problem, you'll have to break it down in the form of map and reduce. Okay, say if you have a word count problem, you will first try to break it down. You'll try to break it down in the form of map and reduce. Okay, the other way to think about map and reduce is like your group by function. You have group by in the database where you first describe the group my items based on this field, and then you define an aggregate function saying this is how you combine the elements in the same group. Okay, so map reduce is like your group by function. Map describes on what basis your data should be grouped together, while reduce combines the values in a same group. Okay, so map and reduce basically the interesting basically you'll have to convert your problem statement into map and reduce. And the most interesting part of this whole game is most of the problems can be converted into map reduce. Okay, most of the problems can be converted into map and reduce. In this case, running only one job tracker become the bottleneck, right? Do we have any backup for job tracker? No, actually. So in case job tracker fails, then you might have to uh, you know rely on some other mechanism. You'll have to restart the job tracker, and then so job tracker is not load balanced. All right, because most of Hadoop has been designed with respect to the batch framework in mind, that this will be used to churn a humongous data which might take few hours. Okay, that way. All jobs will be restarted from the beginning. So the work on a particular job tracker, task tracker will be restarted from the beginning. Okay, not the whole job. So there was a big job. We assigned it to three task trackers. One of the task tracker failed. The work that was given to that particular task tracker would be delegated to the other one. Okay, now let's see this one. Yeah, when the job tracker fails, then the whole process has to be started again from the beginning. In that case, you are right. All right. Now, now at the same time, when we say map and reduce, a file is divided onto multiple machine. The map is being applied on each of this data which is there on each data node, and whatever is the result that gets sorted on that machine by Hadoop, Map gives you the your map function has to be written in a way that it gives out key value pairs. Okay. Key is the sorting key, and the value is the value of the object which will be which need to be brought together. And after that, once it is sorted, okay. So, all right. So let me first answer more questions on job tracker, task trackers. Then isn't that a big problem? Job tracker failing. Why don't we have a secondary job tracker? Like we have secondary name node. Okay. Yeah, it doesn't have basically the objective of the design of Hadoop was for the batch processing mostly, and it's a part of the design the way it has been done. That is why there are other tools which are coming up which have solved those kind of problems. All right. Any questions on job tracker and task tracker so that I can move on to MapReduce? All right. Yes. So name node and job tracker are expensive machines, but they, yes, definitely they can fail, no doubt. So job tracker can fail, definitely, but the way it has been designed basically has been not a very great design with respect to turnaround time, but it has been designed with the mindset of running it, uh, it doing the batch processing. So in case one machine fails, then I mean a job tracker fails, then you might have to rerun everything. And your doubt is correct actually. All right. Yes. So yes. So yes. So Roshan's question is that what are those machines, what are those systems which have fixed this kind of a failure of a job tracker? So one of the big example which we will be taking up in session 9 is our Apache Spark. Similarly, there is something called a Apache Storm, which also executes data in the parallel, but in a different way. Okay. So do these kind of systems like Spark and Storm, they basically have taken care of handling this computing, but they are not designed for this this kind of a job, a background job when you have to churn say 100 petabyte data. Okay. In those cases, MapReduce does a big job. All right. Now, again, I'm back to my MapReduce example. Let's say you have to count the words. That's a standard example. Everybody talks about the same example. We'll go into some more examples on MapReduce. You have a big file containing your text, okay, and you want to do a word count. So that big file, some of the paragraphs will be on first one, some will be on this one, some will be here, right? In form of like block 1 to block 10 are on this machine, block 11, block 12 are here, and rest of the blocks are here, right? Now On this machine, we'll have a logic which says that my key is individual word and my value is say 1. Okay, and this one will do a sorting and will do the counting of the words of its own here itself, and then those all of the sorted data will be merged on a machine, on a separate machine. Okay, all of the data from output of the map will be sorted here on all of these machines and then brought to another machine. Okay, where it will be merged. And your question might be that why is it sorted before sending it for merging? It could have just sent it here. The reason is we are trying to delegate the work as much as we can to the task trackers. Okay. So the output of the map is a key and some value, and then the whole data, those values are sorted together, sorted by the key, and then sorted data is brought to another node where sorted ones are merged together. Okay, you might ask that how does it help? How does it help to sort a data and then merge? Because merging might be a big job. Logic for the each map is same. That's correct. Yes. So you have to, the logic in the map says you will be given input data, and your map logic need to give out the key and the value. Okay. So all right. Now you might ask that, let me show you a few things. All right. Now merging assorted data and still the keeping the output as sorted is easier. Okay, you basically, if you have say 3 data sets from 3 different machines, and let's say there are 3 queues. Okay, let me just try to draw something. Let's say there is one queue, second queue. Okay, so there are there are three data sets which have come from 3 different maps after sorting, and the merging is happening here. So merging assorted data is far easier than sorting and merging together. Okay, so if the data is already sorted, just a second. Hello, hello, hello. Looks like, is it better now? All right, good, good. So I was describing you that merging assorted data is easier than mm, I mean, sorting together. Okay, because sorting takes a lot of time. That is why the sorting happens on each machines. The output of the map is sorted by the key given out by the map, and then all of that is merged together. Now you can imagine that there are queues. You are standing in front of the queue, and in these queues there are people standing by their heights. Okay, there are people standing by their heights, and so on, right? So these these are like sorted data, right? Now if you have to merge these three data sets which are ordered by their heights, right? All you will do is you basically would pick up the first three people from one one each from each queue, right? And then compare which one is smaller, and then take him out and make him stand in the new queue, right? And then you'll keep on doing it over and over again till you finish all the queues, right? That is how the sorting happens here. The merging happens here. Okay, so merging will generally happen on, it is better to have it done on one of the data nodes still. Okay, and it's very subjective. Sometimes it happens on one of the data node itself, or sometimes it happens on the third node, depending on what how loaded are our machines. All right, it all depends on how loaded are our machines. Chandra's question is, even the splits happen after sorting. uh, okay, so these splits, just a word of caution here, these splits are something which have been created out of our blocks. Okay, you can right now think about your splits as if they are equivalent of the blocks from the HDFS. All right, so I did not get the I did not get your question, Chandra. So which split are we talking here? All right, till then I'll just describe what I was explaining. Now after you have merged the data, you have got a single data set which is already sorted. Okay, so you are not convinced about this one? It doesn't work this way. All right. So this is generally called a merge. Heap. We create a heap out of it, and then. So let me take another example. Let's consider the data from each one. There are three queues, right? So first queue containing numbers in increasing order, say 3, 4, right? Now second one containing the heights of say 2, 3, 4, and 8. And fourth one containing 9, 7, and 1. Alright. Now, the first three members of each of this state, the set, these first three members will be compared, and whichever is smaller taken out from this one. So who is smaller out of it? Out of these first three, who gets taken out? Quickly, one, right? And now we take out the one. Now which all will be compared this time? Oh, last one is not sorted, yeah. So let's say 9, 10, and 12. You're correct. Thank you, Puneet. All right. Now, out of this, both twos will be taken out this time. Okay. And then again, two will be taken out. All right. And then these both threes will be taken out, and so on. All right. So this is how a merge sort happens generally. And this comparison for keeping these all element at 3, imagine that there are say 100 elements. Okay. There are 100 rows. Okay. So 100 rows. And these have to be merged together, which means 100 element every time. Here we were comparing 3 elements. If you have 100 rows, you will be comparing 100 elements again and again, right? To make it faster, these first 100 elements will be stored in uh, something called, we call it heap. Okay. Go, I mean, if you have a little bit of time, you might like to read about it, because this is a very pet interview question of everybody when dealing with big data. All right. They ask you, how would you sort this kind of data? How would you merge this kind of data? Okay. So that's how you divide your work of sorting onto multiple machines. You let all these machines sort the data, and then you bring it to one place and merge it. And the way it is merged is the way I've just described you. You pick up one element from all the sorted queues, and then you merge it. All right. And after you have merged into a single one, and remember these are key values. Okay. This also has got some v2 and so on. All right. And so on. Now after merging, there will be multiple values for each key. Those values have to be combined together, or you don't want to combine them together. Whatever you want to do, you describe your logic in the form of reduce. All right. We'll go into the details by taking more examples, word count example and others. But for time being, let's have a look at the another picture which shows you what happens if you have multiple machines running the reduce. Right now in this diagram, there was only one machine running your reduce function, while your map logic has been copied at 3 different machines, and all those 3 machines were running your logic parallelly. First one on one part of the files, another one on different part of the file, and so on. Okay. And the result is combined using your reduce function. Now, the problem with this kind of a design is that one particular machine who is running the reduce function is will might get overloaded. Okay, and in that case, if your machine which is running your reduce function is overloaded, then you say that keep my reduces at least 2. Okay, and in case the reduce function is more than uh, if the number of reduce you want is more than 1, this is what happens. Okay, so on some basis the data is divided on each of the machine itself into two parts, part A and part B. Part A will get copied to one machine, part B will get copied to another machine, and so on. But no matter what happens, no matter what happens here, a key will always go to all the values of a key will always go to the same reduce. It'll not be that few values for a key went to one reduce and few values for a key went to another. Meaning, say there is a key one here, and key one here. All three will only go to one machine. They will not go to half of them went to here and half of it went here. So this is a rough diagram. We'll again come back here and discuss the same diagram in details. Now, is it possible to customize to introduce one more stage between map and reduce? So there are few more stages between map and reduce. We will discuss all of that. Okay. Say for example, combiner, partitioner. There are few more ways that can be introduced here. So the output of the reduce will go again into HDFS. Yes, that is very correct, Chandra. But the intermediate data which is here, say after map, uh, after whatever map generate, that will not be in the HDFS. This data will be only intermittent, temporary, and will be in the local. Similarly, when you copy it, the copy does not happen by the way of HDFS. It is local and direct copy, and so on. All right, does it make sense to you? Is everybody with me? Okay, Ravi, change your setting to public. It's okay to. Okay. Chandra's question is, for how long these output files will be retained? The intermittent one? The final one will be permanent. These go into HDFS. Okay. And will be up to you. If you want to delete them, you can delete them. All right. So Roshan's question is, what happens if the first machine fails? I mean, this machine on which reduce is happening, this one fails. So, so reduce will be attempted once more on the same machine. Okay. But in case machine shut down, then the whole process has failed. Unlike maps, where the map can be spawned on another one immediately, reduce would have that problem. Reason being, reason being, almost all of this data is intermittent, which is required for reduce, and that will get lost if this particular machine fails. Yeah. So reduce is prone to that kind of a failure, though map is fairly resilient. All right. And also, after the yarn architecture, most of it has been made fairly stable. Okay. So Roshan's question is, so won't the intermediate data on 3 map machine be lost? Yes. Yeah, that's correct. That's why I'm saying that in case in case there was this reduced machine which was running the map logic, and some of the maps have finished, some of are yet to finish, and half of the data has been transformed, and that temporary data has been dropped, and if one task fails, then the whole process has to be um, has to rerun, because the temporary data which reduce might be depending on might have been deleted. So in that way you are correct. So in this example, do we have to code around the output file name to distinguish the output files? I did not get. So in this example, so basically when we are running a MapReduce logic, we tell the MapReduce to that this is my map function, this is my reduce function, this is the input file I want to process, and this is the output folder in which I want my results. And in that output folder, it will be storing based on number of reduces. Every reduce will result in a separate file. File 1, file 2, file 3. In a folder, you will have multiple files. Alright, so was I able to answer your question, Chandra and Roshan? Do we have, okay, so yeah. So if you run the reduce again with the same folder name, map will fail. The process will immediately tell you the output folder already exists. And please either you delete the folder or you create, right? Okay. So the question is, how is number of maps and reduces decided? Number of maps is decided by Hadoop itself based on which all machines contain your input data. Okay. While number of reduces is decided by you based on how intensive is your reduce process. All right. All right. So now in Hadoop 1.0, there was HDFS and there was MapReduce. MapReduce took care of both the things. MapReduce took care of running the process job tracker, task tracker here and there, as well as MapReduce took care of executing maps and reduces. Though MapReduce is just a programming paradigm, it was taking care of both parts. The component MapReduce per se was taking care of both parts as doing a resource management, doing a process management, as well as taking care of executing the maps and reduces. All right. So, and the problem with that design, there were multiple problems with that design. First, you could only execute the logic in the form of maps and reduces. Okay. In the Hadoop 1.0. That means if your problem is not convertible into maps and reduces, then you can't do that earlier. So in Hadoop 2.0, the earlier MapReduce was broken down into two parts. One became MapReduce pure paradigm. Okay. And another part became Yarn. Yarn took care of the cluster resource management. In Yarn, the task tracker, job tracker were moved into multiple parts further. We'll discuss those design aspect. While MapReduce took care of converting your problem, taking care of execution of your maps and reduces on top of Yarn. Okay, on top of Yarn. All right, and this made a space for lot of newer kind of innovation. And as of today, you will see that similar to MapReduce framework, there are multiple more. The fact that Apache Storm, Apache, Apache Spark runs on Yarn is because of Hadoop 2.0. In Hadoop 2.0, it made place for other people similar to MapReduce. We have Thales, we have HBase, we have Giraffe, we have Spark, we have lots of many execution framework, not only MapReduce. Okay, that changed the paradigm completely. Okay, so Yarn is more like a framework. I'm trying to answer to Roshan's question. His question is which node runs Yarn? Yarn is more like a framework. So you can think of Yarn as the composition of task trackers and job trackers. Okay, so task tracker, job tracker, and furthermore things are basically part of Yarn. MapReduce gets executed on task tracker, job trackers, right? So the whole so Yarn is a software paradigm. Okay, it is called yet another resource negotiator. It's a framework. It's a design. All right. A quickly, job tracker, task tracker, a part of the yarn. So as I told you that yarn was built in order to support other kind of workloads similar to MapReduce. All right. And then the important part with yarn was anything which people had written for Hadoop 1.0 that just had that was the newer framework was 100% compatible with the older MapReduce logic. So you did not have to rewrite your MapReduce again. Whatever MapReduce you had already, you just recompile them. They'll work on Hadoop 2.0. So from the developer perspective, nothing had changed in the beginning. But afterwards, when newer people realized that similar to MapReduce, they could build another kind of systems such as graph processing systems, in-memory computing, and a lot of other things for which MapReduce was not sufficient. So those kind of frameworks were built. All right. So this is a rough diagram showing you how does yarn work. So as you can see that the task you can see that job tracker is more or less like a resource manager. Okay, job tracker was broken down into a resource manager and few more, while task tracker, which was running on each node, was divided into something called node manager, container, application master, and these keep on communicating with each other in order to execute your task. We'll go into the design of yarn again. All right, but for time being you can imagine it that job tracker, task trackers were further divided into various kinds of systems. Okay, so each container, there is a node manager which is basically similar to a, your task tracker, and is running on multiple nodes, and this container, then application master and all that. Okay, all right. So let's move on to do a little bit more hands-on on our cluster first of all, and then we'll go into the details about how to get started. All right. So did any one of you try to log in onto the Cloud Labs? Okay. All right. So if you are not aware of this, so when you log in into my courses, okay, when you log in into my courses and so everybody was able to log in into LMS, right? All right. Under this, there is an installation instruction, and in this installation instruction, you will see the password and everything for the cluster. And in the installation instruction, it is also mentioned how to set up the virtual machine. So it is up to you whether you want to use the Cloud Labs we will strongly recommend that you use the Cloud Labs, as well as you might want to install the virtual machine. Installing virtual machine is simple. You download the virtual box, you download the Hot&Works virtual machine, and then you import the virtual machine into the virtual box and then start it. Okay. Also, so will there be any difference? I use Cloudera. The Cloudera one actually consumed a lot of disk space for me and was not fast. Okay. Now, so after you have found out the password from the installation document, you can log in into Ambari. Ambari is running on 80 port here, Hadoop 1.nobigdata.com colon 8080. Okay. Here it shows you the whole status of our cluster. It says that data node 4 out of 4 are alive, CPU usage is this much, and overall disk is this much. And here it shows that the yarn's memory usage is this much. Okay, and it shows that our secondary name node has been stopped. Okay, so I have intentionally kept it stopped. We can start it again at any moment of time. And there are task tracker, or you can say node manager, and there is a resource manager, or you can say the job tracker. All right. So Ambari is a nice tool. And also quickly, in case you plan to install, in case you plan to install Hadoop in your organization, my strong recommendation will be to use Ambari for provisioning everything. Okay. So the way it is done is you install Ambari master and Ambari client. Okay. Ambari agent and Ambari server. Ambari server should be installed on the machine on which you want to see this control. This is basically Ambari server. And on all the machines you want to provision, you should install Ambari agent. Like for here, if you want to add a new host, you can add a new host from here itself. You can say add new host and add one more machine into the cluster. And it will automatically install the data node and everything that is required from that machine. Okay. This will take care of lot of hassles of your installation. Okay. So in case you plan to install a cluster, okay, the way, say for example, we are running Cloud Labs, you want to install your own kind of a cluster or running on multiple node. One way is you go to each machine, install Hadoop on every machine, make them communicate and do all sorts of magic. That will actually too cumbersome. The other way would be to use Ambari. Okay. There was something called a Cloudera installer manager, which does a similar thing but was more clumsy. That is why I have preferred Ambari over Cloudera manager. All right. So this is Ambari. Now you might have to interact with the files, any of the services. You can log into Hue. Okay. Log into Hue, and this is how you can see the file browser. Okay. Here, create your own folder to work because there are too many folders here. Okay, create your own folder and keep your files inside the file system. All right. So let's take a 10 minutes break and then come back. Hello, I'm back. Should we start now? All right. So looks like there has been quite a conversation here. Let me have a look. Okay. All right. It was 9:42. Guess any idea about username and password to log in to you? Okay. So Chandra, you were able to log in? All right. Okay. So to see the status, you can go to Hadoop 1.no big data and 8080. All right. So the account you have is not admin. Is just another user in Ambari. Okay. With respect to Ambari, that is why you cannot provision anything. You will not see some of the features. All right. Here, but you can see clearly that it shows you the whole status of the cluster. Okay. Whole status of the cluster. How much of memory is available at name node and all of this. All right. How was the network usage at what times? So this way you can have a look at it. So the password is student and the other one, it must be shared. I'll not be saying it here right now. Okay, it has been shared by Puneet in this session. You can have a look at that. All right. All right. So that the password login is same. So this is one way from the browser side. You can see this, and this is like standard setup. Okay, standard setup with a minimum number of nodes. So whenever you are generally setting up Hadoop, the minimum number of node is generally something like 2 to 3. Although people set up on virtual machines also, but that's just for testing, and that is not something which people do when it is in production. Okay, virtual machine is fairly useless when it comes to the computing, just to get you acquainted, that's all right. There are few things which might seem to work on a virtual machine but may not work in the real cluster. I'll give you a couple of examples in the sessions where lots of people think that uh, start thinking that okay, this is how it works when they're using virtual machines. Okay, say for example, we'll talk about Scoop uh, in one of the sessions. In the Scoop, uh, I mean that gives a very virtual machine gives a wrong impression. Okay, that way you can use either one. Okay, you can use either one, and it is absolutely up to you. All right, but it is strongly recommended that you understand the Ambari. Okay, all right. Now let's try to do some things. All right, the data and the architecture wise here, you can see that there are 4 nodes Hadoop 1, Hadoop 2, Hadoop 3, Hadoop 4. These are four different machines with four different IP addresses. And first one has 4 GB RAM, second one is 2 GB, third one and fourth one is each 1 GB RAM. And these are the components installed on all of these. Okay. Along with that, we have installed R, Python, and other generally required tools, including Spark, on this. All right. Now here you can see here that these are the various clients installed. What I wanted to show you are the services. Right. Now under services, you have got HDFS, Yarn, MapReduce framework, and then you have Days, and then HBase, Hive, and so on. Okay, coming back. Right. So Ambari, which is running on 8080 port, manages the servers. Hue is for interaction, specifically for things like copying files. Okay, for things like copying files and all. All right. Now the next way of communicating with machines is by logging on to the cluster. So cluster is are nothing but Unix machines. So you to connect to any Unix machine, you can do SSH. So you can do SSH Hadoop 1 dot no big data dot com. Okay. If you are on Windows, sorry, you if you are on Unix, you have to say SSH this. If you are on Windows, you can use something called putty. Okay, putty, and then you log in. Now I am basically on the server called hadoop1 dot no big data dot com. Okay, here while working, create your own folder using mkdir before starting to create any files. All right, you can say make mkdir and your directory, and you can do. For example, I have my own directory here as Giri, and I cd to as Giri before I create anything. Okay, avoid deleting files because uh, there are files from other people who might be using them now, and try avoiding stamping on anybody else's feet. Okay, and the single login has been kept purposefully. First, in order for all of you to see other people's work, to understand what people doing, and other is to, because sometimes it becomes easier that you put a code here in a folder, and then drop an email saying my code is located in this folder, can you have a look? If you don't have permission, then it'll become a problem. That is the reason we have kept a common place for all of us. Okay, so this is a Unix server where we have logged in. Okay, so in case of a Hadoop, in case of a putty, you should give this host as hadoop1.no big data, as well as you can here you can also say hadoop 2 here, hadoop 2, hadoop 3, or hadoop 4. Okay, those are different machines. So this is, there are too many files actually. I'll clean it up today or maybe soon. Do not touch anybody else's files. All right. Now, from the command line, from the Unix command line here, you can talk to HDFS. How do you talk to HDFS? Using a command called Hadoop, and then first argument is ls fs, and then the next one is using various kinds of uh, HDFS commands. So this was ls. So this folder structure you see is in HDFS. Okay, these files are in HDFS. Same HDFS is also visible from the hue. Okay, so if you create a folder here saying create a directory called my random directory. Okay, so here you can see that if I say ls my random, or you can say ls again, and so ls as in Hadoop fs minus ls. Now you will see here there is a folder created over here, right? So that is HDFS. So keep in mind when I say local ls, this is my local file system of Hadoop one. Okay. If I create anything here, I'm going to create that file only on the local machine. Okay. Not on the HDFS. All right. Similarly, if you have right now I'm logged in into Hadoop one, I can exit and log in into Hadoop 2. I can create some files over there. So those files will be on Hadoop 2, similarly Hadoop 3. But any file I'm creating using HDFS, meaning Hadoop fs minus la, okay, here, those will be visible no matter which machine I'm logged into. Sound sensible? Okay. So, and let's say I want to copy some file from local. Okay, let's say we have a file. Let's just create a file. How do you create a file? Using nano my my file and say 21 fab.txt. This is a test file and this is located here locally in Asgiri and this. Right now this folder, so this is this for although there is a Asgiri folder on HDFS also, but this file which I have just created is located locally. That's why you will not see it here. But if I say Hadoop fs and I say copy from local, okay, my file 21 fab, okay, and I say into Asgiri folder. Now this file will be copied from my local machine. Local machine when I'm talking is my current machine Hadoop 1.no big data. Okay, if I say host name, so my current machine is Hadoop 1.no big data. That's where I have SSH'd. Okay, now I have copied this file, my file dot this, onto the file system HDFS under a folder called Asgiri, which means if I go now into Asgiri folder, if I refresh it, it should display. Okay, you can see that the file is here now. Yeah. So Chandra's question is, what is this nano used VI? So if you are comfortable with VI, I'll recommend you the VI. Okay. But the problem with VI is lots of people have a those who have not used VI, it will have a little bit of a learning curve, while an editor like Nano has a little less learning curve but is not as powerful as VI. But if you are a developer, and it is, I would personally recommend you to learn VI. Okay, and yeah, so now we have been able to copy the file. Okay, now if you want to see more commands, to see more commands, you can just say minus help and you will see the all the commands. Okay, Hadoop, these are Hadoop commands. Shows you there is something called cat. Cat means printing the file in onto the terminal. Then there are standard command like chmod, because HDFS also comes with its own permissioning, similar to Unix. Chowner. All right. So these are the various commands of HDFS. All right. So have a look at all the commands provided by Hadoop FS, and then you will have a clear idea as in what all could be possible. Okay. All right. Any questions still here? Any questions? All right. So moving on. So we're able to copy a file from local, and okay, this I will avoid right now. Okay. Now there are various commands other than uh, and any command you want to execute, you can actually execute from here. Say tomorrow we'll be learning something called Hive. So you can start Hive from here itself. Hive is, as we told, is an SQL engine where you don't have to write your code in terms of MapReduce. It converts your SQL queries into MapReduce. Similarly, there is Pig. Pig is also similar to Hive in the sense that you code in terms of a SQL-like language, and that get converted under the hood into MapReduces. All right, and then you can also talk to HBase. Okay, by typing a command called HBase shell. Okay, and you can also work on Python here or any other language. Okay, so we also have R. Okay, here you can start working on R. So all of that is available using the command line itself. All right, and all the commands, whatever we are talking about, scoop, flume, everything is installed on these machines. All right. Not in this session. R is some language, though some of you Some of the people in my class are generally from a background of data sciences. They generally like to work on R, and that is why I told. Okay, R is a programming language for churning the data. I'll not be giving an introduction to R in this session. All right. If you Okay. Now let me show you how to run a MapReduce. Okay. How to run a MapReduce. So this is the general one example that comes with. Let me increase the font here. All right. So first you say Hadoop, that is the command. Instead of fs, this time you say jar, and you provide the jar that contains the logic of MapReduce. Okay, then this is the argument you're providing to the jar, this program. Okay, and this is another argument which is basically your input folder, and then this is your output folder. So let's try to run it. Okay, so you have a Hadoop command to which you are passing an argument called jar, that you are inclined to run MapReduce rather than talking to HDFS. If you want to talk to HDFS, you type here fs, Hadoop fs, and then the argument. This is the jar file which contains the logic of our MapReduce. Right now we are interested in word count. So one of the example is word count in these examples, which are provided by this words with the default installation of Hadoop. Now next is the folder containing our input data. Now, yeah, that's a good point. Let's have a look at our input data. Right. So the easiest way is to go to this place. Okay. And I prefer this way. So I went into this folder here from the browser. You can see the input text file. It's basically a big file containing lot of text from here and there. Okay. Basically, it's a combination of around 8 books by Condell, Sherlock Holmes essentially, and so on. Okay. So this is the input data. This is the first page. You can see the whole file. If you want to download the whole file, you can download from here. And this will come to your local machine, your desktop. All right. Now, so this basically does a word count. This example does a word count in this input text. So let's start the process. Okay. Let's see what happens when we run this. It says output directory exists. Okay, as somebody was asking in the session, it says that output directory exists. So let's first delete output directory. Hadoop fs minus rm, and we call minus rm minus r, and then we say okay. So we are trying to run a MapReduce job, and for that we are using a Hadoop command line. These are the example. The MapReduce job is to do the word count. Okay, and this example comes with the Hadoop itself. We're trying to run the MapReduce job provided by the Hadoop installation to do the word count. All right. So we'll talk about it later again. So generally, whenever you are dealing with technology, you generally go back and forth multiple times. Okay. Now, the problem as we are running it, the problem we are facing right now is this folder already exists. So let's first delete that folder. Okay. Yes. So the word count program has raised an exception saying that the so no, it's not word count program that has raised the exception. It is the Hadoop command line that has raised the exception. Before starting the process, Hadoop command line checks, and if it already exists, then it gives an error. All right. So we say Hadoop fs minus rm minus r, and we say yes, that's correct. Right. So now that has been moved to trash and has been deleted. Or you can do the same operation of file manipulation from the browser. Okay. Now let's run our example and see what goes on. So this is how you typically launch a Hadoop program. Okay. Though in production environment, in a large program, okay, in a large program, when you have multiple Hadoop jobs, there are a lot of things. You run the whole process via a tool called Uzi. Oh, is it? Maybe somebody is unmuted. Okay. Now you can see that the job has finished. It started maps first. Once map got finished, then reduce was started. And afterward, when both the things completed, then it finished the job, saved the output, and as well as the things which you should notice is the tracking URL. So whenever you launch any MapReduce job, no matter how, it gives you a tracking URL. The tracking URL gives you the detail about your maps and reduces. Okay. So there was a task called map type. There was these were the first attempt, and the first attempt was successful. Under the logs of this attempt, you will see all the things. If you are if you have written your code of MapReduce and you are printing on standard output, say system.out.print, or you are printing to the screen, that will go into these logs. Okay. So rather than hunting for logs on each of task tracker, each of the machines, this place, which the URL which is provided by Hadoop when it starts up, is a very useful thing. Okay. All right. Now let me try. I'll take your questions in a minute. So here you have it shows you all the detailed operations, and whenever we'll be doing a little bit of optimization, we will notice all these numbers. It shows you how many tasks were run, how many records were read, what was the network traffic, how much memory was consumed. All of this will be detailed in this statistics. All right. Now let me ask. So do we have to create a separate directory every time we run? Yes, you have to. Okay. Or you can delete the older one and then you can use. All right. So now let's say we are trying to write here. Okay, again the same thing, it'll give us an error. So it just so happens that they have taken a call on having, instead of overwriting the data, so separate output directory. Okay, because this is going to write the data into that output folder. Okay, so there could be only two things. Either it silently says, okay, I will overwrite your data, or it could give you an error that the output folder already exists. Okay. Because the file name inside output folder, let's have a look at the output folder. Okay. Now, this is where did we save the output? User student word count output part. Okay. user student, okay, here user student word count, user student word count. Do you see any word count? UVW, maybe next page. Okay, here is user student word count. Why can't I see user student word count output? So in production, do how do we keep it doing? Yeah. So every time when you build your fold, where did we store the data, by the way? Just a second. It's inside Asgiri. Sorry, it's inside Asgiri. And how did it become Asgiri? I don't know. Okay. So let's have a look at the output first. Okay. Then I'll answer your question. It's coming. Okay. So here you will see that there is a part R this. Right now I'll have a look at it. It has done a word count computation. Okay. All right. Now every word, whatever words are coming, we'll see how can we make it better. Right now it's also taking into consideration these special characters. All right. Now, all right. So now you notice that for each reducer you will have this kind of a file name. If you had two reducer, then you will have one this and other would be something like part minus r 00001 and then 2 and so on. Okay, so that kind of file names are there, and that is the reason instead of creating because that's the reason it want a fresh folder, because the file name of each reducer is going to be same. If you have five reducers, there will be same name. It will be always part minus r 000 and then a reducer number. That is why, since the output file name is not randomly generated or every time new, that is why it gives an error by design. So now answering, yeah. So let me try to answer two questions here. So we did not code ourselves to this reduce map reduce to make it fail. It's the Hadoop which fails, which Hadoop command line, which is by design, fails in case the output folder exists. Second question is, how do we do it in production? In production you always, because these are more like batches. Every night, it's a very good question. Every night this job is going to run. Let's say every night you are doing a word count, new data comes in, you create. Now every night, if this happens, what you do generally is either you create output folder based on a timestamp, okay, or you remove the older one and then you do this. And which brings us to another point, that in production we do not do things manually. We generally create a Uzi workflow, just like Apache Ant, and in that we create this workflow that first delete the folder, then create another folder. Just first delete the folder and then run Hadoop job. Okay. All right. So I hope I have answered your questions. Have I answered your question? All right. Yeah. So we'll show you the word count program in a very quick one. Yeah. So, all right. Don't worry about that because that's what I wanted to hear from you. Basically, you when a student start asking for the code, it means that we are ready to move. Now let's move on. Okay. So we'll show you the logic and we will also try to understand how to build various kinds of program. Before that, let me ask you very simple question. If you have a plain text file, okay, imagine that the same file which we just showed you, like if you 8 books or 9 books, how would you find the frequencies of words? Meaning, how many times a word has occurred? How will you find that? Okay, this is probably pretty easy. So, anyone? Slice the content. No, whatever way you want to do it, how would you do this? Okay, whatever way. Imagine that in an office, somebody asks you to do this. Whatever possible way you can think of, you should answer this question. Whatever way, whatever way. Except for the answer, like I will delegate it to my subordinates. Okay, so, right. So, okay. So I've got great answers. And yes. So whatever program, algorithm, tool, technique, whatever you want to use, you use that and find me the frequency of words in this book, in this set of books, which is plain text. The way I had showed you my data in the same fashion. Okay, this file, not this, the input file, this one. Okay. So it's a not very big file. It's just few MBs. These steps will be good enough. I do not want it to be formal one. All right, let me copy paste stuff from the chat. All right. So Murugan says slice the content using a token and keep it in an array. Good. Write a logic to count for similar words. Good. Okay. And that logic should be how? How should that logic look like? Then Prithvi says pick a word, count its occurrences. Okay. That is also an approach. Roshan says basically group by distinct words. Good. By sorting data and count. Good. Separate file by space as a separator and sort and then group. Good. And repeat until all words are done. So that is Prithvi's one. So pick a word, count its occurrences, and then okay. So and then keep on doing that until all the words are done. All right. All right. Do you think it is what is the complexity? How many times you have to compare word? If you have n total records, how many times you are going to compare total number of comparisons? To count each occurrence, you'll have to do one comparison. N to the power n. No. Oh, right. It is not n to the power n. It's n square. It's n into n. Yes, eventually we'll get the results. But imagine this. If you have a million words, your program will take quite some time. And here you have million words. Even for this file, what we are talking right now, it might take few hours. And that is the trick behind almost all the computations. Okay, so Prithvi, you should try doing it. I'll also try doing it, and I'm actually interested in showing you that this is the actual reason why I was trying to say that the problem with sorting is these are the things. Okay, and you will be surprised at how slow it could go. Now assign each line to a variable and look for a word if it exists plus else 0. Sort and count consecutive matching word. Good, good. And yeah, so any other answers than this one? Hmm. Sort the array, then start the first word until good, good. So we have got 3, 4 answers which are on this line. So we'll talk about all of this. So first approach is create a frequency hash table or a dictionary. Okay. So a dictionary is something like a big, place where you store keys and values and retrieve keys and values. Every programming language has some connotation for hash table. So you created this dictionary in which you are going to keep on adding words or increasing their counts. So it has word and their counts as value, and word is the key. So you iterate over the file, you store a word into this dictionary if the word is clean. If the word does not exist already, you add that word into the dictionary. If it already exists in the dictionary, you just increase its count from 1 to 2, or increase its count by 1. All right. So is this approach clear to you? And when no more words left in the file, print the hash table. Is this approach clear to you? So do you see any problem with this? Do you see any problem? How can we parallel this approach? Very good point, Prithvi. If we are if they are all unique, you write all the data. Yeah, that's correct. For each word, you have to scan both input and the whole dictionary. That's good. But the dictionary is generally quite fast lookup. Okay. So you are iterating through the input, picking up one by one, keep on adding the words into dictionary or just increasing the count. So so input has to be scanned only once. Each word has to be visited only words in case of input. You don't have to scan whole file for each word again and again. And with respect to dictionary, it's quite fast lookup. So any other approaches? A- any other problems you see with this algorithm? All right. So yes, the biggest problem other than how can we convert this into a parallel approach, other than that, the other challenge we will see is, so dictionary is generally indexed. Whenever we say hash table, that's actually an index one. Okay. Index, I mean, that's really, really fast access. The problem with this approach is, the problem with this approach is the hash table has to be kept in the memory. And that becomes a very big issue when the data grows big. As the data starts growing bigger, these kind of approaches start faltering. And you will be surprised how many people actually make this mistake when dealing with big data. Even the experts, when I looked at few people's code, they ended up doing a lot of things in the memory, even though data was bound to grow. Okay. So here, the hash table is quite memory intensive. If the if the actual content of the file grows to say 5 GB, you will require a 20 GB RAM because hash table takes approximately 4 times the memory of the actual one. Okay. So that is the problem with this. Second approach, somebody told me in this group itself, why don't we do that using SQL, using group by, right? So this approach is good part about this approach is that it's not memory intensive. Databases have already figured out a lot about handling the memory. So churning say 100 GB data will not be an issue using this command. Okay. Select word comma count star from table group by word. Right. So you break down one word per row, and then you do a group by. Sounds good? Any if you have any other approach in mind, you should just type it. Any other approach do you have in mind? Are you guys with me? Do you have any other approach in mind? Okay. Divide the file into multiple parts. Good. Create multiple threads to handle each parts and follow the count approach mentioned in your slide. Okay. So what you're saying is slice this file into parts. Let individual thread count the words independently, and then you merge these counts at a single place. That's what you're saying, right? Okay, that's a good approach. Yes, that's a good approach. We'll reach till there. Now, this third approach does not have any memory problem because database have figured out all of it pretty well. Okay? Yes. Now, third approach could be using a Unix approach, meaning do a cat file 1, file 2, replace the tab or spaces with a new line, and then sort it. Sort the data, and then use a command called unique -c. Okay. So, okay, a little bit survey. I want to understand how many of you are okay with Unix. So you can figure out this command. What does it do? Okay. So this is basically a simple command, simple pipeline of commands. Okay, I'll just copy paste it here. I will go by one. This portion, this particular portion says concatenate file 1 and file 2 and give the concatenated output to the standard output. Okay. Now this command says whatever input I would get, I will replace space with a new line. Okay, white space with the new line. This is what this command says with the regular expression. You should go through a regular expression session which is there on the first session 1 videos. All right, to understand the regular expression, it is very much required. This is a regular expression, just like wildcard characters. It says that one or more of the spaces should be replaced with new line. All right, now which means it's basically breaking a line into multiple lines, one word in each line, right? After that there is a sort command which says that sort my input data by using only a memory of 1 gig size. And after that, once data has been sorted, you use a command called unique, which basically counts number of unique words in the input. All right. By now, you must have figured out that this pipe, which you see the vertical bar, it basically takes the input from this side and gives it take the output from the left hand side and gives it as the input to the program on the right hand side. Okay, so the pipe basically is taking the data, taking the output from this command on the left hand side and giving that as an input to the command on the right hand side. Okay, so cat significance of cat is it takes a file just like in DOS. You had type command which could read the file and give out the data onto standard output. Okay, if you do not place a pipe over here, if only you type this command, it will just give the data onto the screen. Okay. If you put this, whatever was supposed to come to the screen goes to SED. Okay. So file 2 is if you have two files, if you are counting in multiple files, that's the only reason I have kept file 2. Okay. That's all. So this is the third approach in counting the words. All right. Basically, here the most important part is this command, which shows that, which is basically able to do stuff, able to sort the data using a smaller memory. Now, so problem approach number 2 and approach number 3 solve the problem of the memory. They do not exhaust our RAM. They are able to handle the RAM. I mean, they are able to handle if the data is far beyond the RAM, right? Do you see any problem with the approach 2 and approach 3? Approach 2 was SQL, approach 3 was Unix, approach 1 was a code. Good, good. So Chandra is saying that we could make it further better by using a command called parallel. All right. So there is a way of running these things in parallel in Unix. Okay. So that's a very good point. Any other? All right. So moving on. So now after what will happen is as the data will start growing, IOs will become the problem in Unix as well as SQL. Okay. First, IOs will become a problem, and then the CPU, then the network speed. Okay. As the data keeps growing big, these kind of problems will come into play. All right. If you have 5 computers and you have few terabytes of data, say 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 20 terabyte of data, is still breaking for all my voice? Yes. All right. So if the data starts growing bigger than further bigger, first your network will become a problem if your data is stored on the network. Second, the disk space will become a problem. I mean, because disk space became problem, we moved the data to network, and then IOs will become a problem for you, right? So what do you do? Then there is a fourth approach. Yeah, the system load, because one machine won't be able to solve your problem. So you use something called external sort. What you do is you ask first machine to churn your data, and then also ask machine 2 to churn the data and then merge it and give the output. Okay. You do it manually. So this is a very decent approach, which we do it quite often. The only downside about this is anyone? So in this approach, what we have done is we have asked machine 1, we have given machine 1 an input data and said, can you give me the counts? Machine 1 gave the launcher back the counts of the words. Similarly, machine 2 was also given a set of data by the launcher, and then machine 2 also did the count. And now launcher will merge it. Anyone? Okay, yes, we have to come up with a splitter and merging program. That is correct. Any other? That is correct. That is right. This data is going from launcher to machine 1. This data is going from launcher to machine 2. Do you see a problem? All right. Yes. Yes. So problem with this approach is, first, there is a lot of time that was consumed in transport of the data. We are sending the data again and again. Second, for each requirement, so for each requirement, we have to keep on building this code. You'll have to keep on building this distributed computing program, which will keep on delegating the work. And as Chandra was saying, that in case one node goes down, then our data is lost. So, which means you will also have to build all of this kind of logic, that in case one goes down, send it to another, and so on. So the fault tolerance has to be built in, and that would require a lot of engineering in itself. Okay, that would require a lot of engineering. Okay. Hello, hello. Is it audible? Is it breaking still? Okay, I hope that it doesn't break. All right. So to build this kind of system, you every time a new problem comes, you'll have to keep on building it again and again. Okay. And a lot of time is consumed in transport. All right. Therefore, the solution is MapReduce. There, that is why you use MapReduce to solve your problem. Okay. The solution in this game is, we talked about four approaches, and out of four approaches, MapReduce is probably the best. Okay. Now, what exactly is MapReduce? MapReduce is a programming paradigm to help you solve big data problem, specifically the jobs that are sorting intensive. That job that requires a lot of ordering of the data. All right. And you only have to code two functions, map and reduce. Map converts the input into key value pair, and reduce aggregates all the keys, all the values for a key. And MapReduce as a paradigm is used by many systems, including Cassandra, MongoDB, CouchDB, and a lot. As a concept, they all have their own MapReduce mechanisms. And MapReduce can be written in Java, Shell, Python, or any binary. Okay, by the way of something called streaming, Hadoop streaming library. All right, so even in MapReduce, we have to come up with separate program for every requirement. That is very correct. Infrastructure can be reused, but okay, yes. Chandra? All right. So in the fourth, if you see, launcher is sending data to machine, right? Every time. While while in case of MapReduce, the map goes to the data. So transport of data is heavily minimized. All right, let's have a look at the code the way we would code a MapReduce. Yes, you're right. Sending code to the data instead of data to the code. Instead of bringing the wood to the X, we are taking the X to the wood. All right, that is the difference. To cut the wood, instead of taking the wood to the X, we are bringing the X near to the wood so that we don't have to transport the wood. All right, to process it. Similarly, we are taking the code to the data. That's correct. All right, now let's have an example of a MapReduce. Okay, we'll just go one step at a time. Imagine that you had a text file containing sa, re, sa, ga, and you wrote a map function which takes the input, and for each word, all it prints is a key and a value. Okay, which means we will have sa1, re1, sa1, and ga1. Alright, that is the job of our map. This is the code which is written by us. Okay, it'll be your responsibility to spit out the to write a code that spits out the key and the value. Alright, now this key value is taken by Hadoop and converted into this format: key and values. Key and values. Whatever value you have given, if there are duplicate keys, it will bring all the values together and then feed that to a reduce function. For each key here, our reduce function will get executed. So reduce will get key and an array of values. Alright. Now in this reduce function and the body part, you will have to figure out how to combine these values and return that combined value. That's going to get stored. Sounds good? Is this example clear to you? And that is how we counted number of words in the input. Are you with me? Is it clear to you? You wrote a function map which converted the input line into key value, and you wrote a reduce function which converted the full array into the summation of this. Okay, this is more or less a pseudocode. Is more or less a pseudocode, and that is how this dashed line you see in this diagram is the job of the Hadoop. Okay, now let's have another look at it. Now, in case you have multiple maps, so first map is on one node, another map is on another node, same code is getting executed on both sides. This will get converted here and this will get converted here. Okay, and after that, when the merging is happening, okay, in the step number 3, this is sorted, this is sorted. So here, so after sorting, the merging will happen, and after merging, you will get something of this sort, and then reduce will be executed on it, and you will get the output. Sounds good to you? Yes. So only two guys are awake, or have I put everybody to sleep? Okay. I think. Okay, Santosh is awake. All right, all right. So there we are. Good, good. All right. So okay. So I have not put everybody to sleep. The people are awake. Now the next step is, although the diagram is little bit incorrect, but conceptually this is what is happening. Here in the first step, map ran and it gave key value pairs. Then here also it gave key value pairs. Then the sorting happened like this. Okay. So after sorting, our keys got ordered. And after that, in the fourth step you see, the in the fourth step, the shuffling has happened. It merged and shuffled. What is the purpose of merging and shuffling? So, merging means they all keys will be brought together, and shuffling means some of the keys will go into one reduce, and other some of the keys will go to another reduce. And after that, okay, after that they are merged. They are counted, and then they are reduced. After that reduce is done, and yeah, so we have two reduces, same function cloned twice, running on two different machines. All right, that is how the multiple reducers work. Okay, the another way of looking at map reduce is thinking it as a group by clause. Select word comma count star from my table, group by a word. Okay, that is, here you can see that when we say that group by word, okay, is equivalent to saying here that my key is the word and then group by. Okay, the moment you here in the group by clause, this line specifies that we are interested in grouping our data by this particular word. Okay, that's what this line says. Similarly, our map function says I want to aggregate all the values in the key based on this particular key. And a reduce function is equivalent to this aggregate function here, which is count star, or might be sum, might be anything, which basically convert an array to a value. All right, which basically converts an array to a singular value. Sounds good? So now there are few assignments for tomorrow to all of you. Okay, you do not have to write any code. All you have to tell me what will go inside your map and what will go inside your reduce. All right, based on today's discussion. So okay, let me answer Roshan's question. So we'll talk about shuffling. There is something called a partitioner. Partitioner decides how to divide the data multiple reducers. Okay. Objective of shuffling in this diagram is to divide the data in multiple reducers. Okay. We'll talk about something called partitioner in the next session. All right. Now here we go. All right. So we will discuss more into detail about this. Okay. Here all you have to do is on the pen and paper. On the pen and paper, you just mention that given this input file, my map will give out this is the key, this is the value, and my reduce will do this with the set of values, just in plain English. Okay. Find anagrams in huge text. Okay. First one is just find the frequency of letters. Do you require map reduce? It's a theoretical question. First, you justify whether map reduce is makes sense or not, and then you write it conceptually that this is what it is. The key should be this and value should be this. All right. All right. So yes, frequencies of a letter in a file. So given a file, do you require MapReduce to find the frequencies of letter? If so, then why and when? And after justifying, write down what will go inside map, what will go inside reduce. Now, second question to all of you is: you are given a huge text, and you have to find anagrams in it. Okay, you have to find anagrams in it. What is anagram? Anagram is basically a twisted word. For example, a twisted as in a rearrangement of the letters. It is not, anagram is not palindrome. Palindrome is something which is same from both the sides. Okay. TAT is either you read from the beginning or you read from the back. It's the same. That is palindrome. Anagram is rearrangement of the letters of the word. Okay. Say for example, cat, tack, and act are just rearrangement of the same set of letters, right? So you have to find anagrams in the input text using MapReduce. Okay. You have to bring no, the words don't have to make some sense, they just have to exist in the file. Okay. All these words which are anagram, they should exist in the file. So for example, in this file, the does not have anagram, so the is alone. Cat, act, and tack are, although they don't make much sense, but still they exist in this file. Okay. And also notice that ATC is not in output. Okay. Where did my stuff go? All right. TCA will not be valid because TCA does not exist in this file. And basically in this file, bring out of this file, out of a given file, you have to bring all the anagrams together. All right. Now, third question to you is: there is a file that contains DNA sequences of all the people in this world. Find out the people who have same DNA. Okay, so the file input, sample input is user1 ACGT and so on. So here you can see that user1 and user4 have same DNA, ACGT. User2 does not have a matching DNA with anybody. User 3 and user 5 have matching DNA and so on. Okay. What will go in the map, what will go in the reduce, you will have to write that down. Okay. Based on today's discussion. Okay. Now, next question is little tricky. Some researchers found that all the people who have either identical DNA or the mirror image of the DNA, they belong to the same family. Now, given the input containing the user and the DNA, bring people from the same family together. Okay. For example, user 1 and user 2, they are mirror image of each other. So you have to give output like this. And user 4 is identical as user 1. So user 1, user 2, and user 4, all three of these have all three of them belong to the same family. Is this clear to you? All right. Now the fourth question to you is this. There is an unusual democracy where everyone is not equal. Okay. The vote count is a function of the worth of the voter. Though everyone is voting for each other. In this democracy, people vote for each other. Okay. Now, the total value of the vote count is summation of the worth of all the people who have voted for me. My total worth at the end of day, my total vote count at the end of day is summation of all the people who have voted for me, the summation of their worth. Okay. For example, if A is of the worth 5 and B is of the worth 1 are voting for somebody called C, the vote count of the C would be 5 plus 1. Okay, A and B voted for C. A's worth is 5, B's worth is 1. So the C's total count will be 5 plus 1, which is 6. Okay, or you can look at here. A voted, so C voted for F and C's worth is 11. So F vote count is 11. All right. While A and B has not been voted by anybody, their vote count is 0. All right. So these are the 4 questions we'll discuss tomorrow. But till then, do your homework and come up with a rough idea. Like this should be key, this should be value in my maps, and these are after I have done with first set of map reduce, take the file and again feed to the next set of map reduce. You come up with all those kind of ideas. All right. So these are the 4 problems we would take forward tomorrow. Okay. But till then, do your homework and also finish the assignment as mentioned in the course page. Okay. Here you have quiz. Okay. And you have installation instructions. And there is a regular expression session. Presentation of regular expression is also there. And in the second session, the assignment subjective question is also available. Okay, come here and then you can write the assignment. All right. So answer there in the on the website itself. That is more manageable. All right. So let's meet tomorrow at the same time. All right. Thank you very much. I enjoyed the session thoroughly. I liked your questions. Okay. Thank you, Puneet. Let's meet tomorrow and take it further. All right. Bye bye. Have a great day.